G'day guys, welcome to video 5 of topic 2, and we're going to look at some circular motion examples in this one. So the goal of this is just to go through the worked examples of chapter 3.2 and 3.3. Hopefully each question should be relatively self-contained, so you won't need any techniques I use in an earlier question in order to figure out a later question, so that way if you're having trouble sort of puzzling out something similar, you should be able to skip to just the similar worked example and get the background theory there. So here's the same learning attention and success criteria as our last video. You can see we've done these first two in our previous one, but now we need to finish off this last bit where we need to solve some problems. Again, the same KS table there, so nothing for you to do. So let's delve right into it. Let's have a read. So this is 3.2 worked example A. A girl whirls a ball on a string on a horizontal circle. The length of the string is 2.2 meters and the time for one revolution is 3.1 seconds. And I've got a few things we're going to calculate there. Now I always like to draw this situation to help us ponder what's going on. We have a girl. I'm going to draw it top down though, so it's horizontal. So here we have our girl in the middle. Let's just put G for girl there. And we have a ball on a string. There's our string, there's our ball, and it's going around in my horrible circle. Now the length of the string is 2.2 meters, so this thing here has a length, we'll call that R for radius, of 2.2 meters. Okay, so remember the radius is the distance from the center where the girl is to the edge where the ball is. We hear here that the time for one revolution equals 3.1 seconds. Okay, so what we're asked to find, the first thing we're asked to find is the period. Now the period is the length of time it takes to complete one revolution. Well, conveniently enough, they've given it to us. We're told that it takes 3.1 seconds for one revolution. That is indeed the period. So let's put that equals capital T for period. We want to know the average speed of the ball. Okay, now the average speed of the ball, remember, speed equals distance divided by time. Okay, we know the time it's actually going to go. It's got 3.1 seconds, so that's going to equal something divided by 3.1. The question is, what's the distance? So the distance is how long it takes to go all the way around, or sorry, how far it takes to go all the way around in one revolution. We're using this t equals 3.1. So now we need to know, well, what is this circumference? What's the formula for circumference of a circle? We know that that equals 2 pi r, and the good thing is we have r in this case, so we're going to have 2 pi times r, which is 2.2, and we can plug all those things into a calculator. We'll get an answer. 2 times pi times 2.2 divided by 3.1 gives us a speed of about 4.46 meters per second. So that's our average speed. Now the last part is, well, what's the velocity of the ball? Okay, remember the velocity is going to change its direction, right, because it's going to be going around. The speed doesn't change, the speed is the magnitude. But the good thing is the velocity is equal to the speed in this case, because at any one point the direction is going to be perpendicular to the radius. So we're not really able to give a direction in this case, but we do know that the velocity will be equal to the average speed. Just because this is uniform circular motion and it is not changing. If we had non-uniform circular motion, then we'd have to try to work out this velocity based off of other things as well, probably centripetal acceleration, etc., etc. But in this case, it's just going to equal 4.46 meters per second, not squared, meters per second. Okay, so in this case, most of these are pretty straightforward in that you have your speed will require a little bit of information about the physical properties of it, but in this case the good thing is they told us what the time was directly for one revolution. You won't always have that. You might get given something like the time to go halfway round the circle, or you might get told that while it's spinning in circular motion it goes 1 meter in what's the word I'm looking for, 1 meter in the actual in a time of like 1 second, but you don't know the actual radius, so sorry, you don't know the actual circumference, so you've got to work that out in order to figure out, well, is this a full revolution or what? So you can make it a little bit more complicated, but in this case we're just dealing with the idea that some of these terms will be pretty straightforward. Okay, this question here is a much simpler one. We're asked to calculate the period for an object with rotational speed of 30 RPM. So we want to know, let's put my pen up, sorry. We want to know t equals what? So we have here rotational speed, 30 RPM. 30 RPM. So, we don't need to know the size of it. Okay, well, let's just think about what this means. This number here means that it goes 30 loops per minute. Okay, or let's rephrase that, because we need this in seconds. Period is the is a unit of time, and so it has this SI unit of seconds. So let's go 30 per 60 seconds. So how long then does it take for us to do one? If it's 30 per 60, what are we got to do here to figure out how long it takes to go one? Now, we did give you a formula in the theory one, and we could jump straight to that. Remember, the formula is t equals some smaller time divided by the number of revs. Okay, and in this case the time is just going to be 60 and the number of revs is 30, and so we can see that this equals 2 seconds. Let's see if we can work this out intuitively though as well, so we understand why this formula comes out. So 30 per 60 seconds. Well, let's reduce that. Let's figure out a common factor. Well, we've got 30 and 60, so that means it must be 3 per 6 seconds. Okay, so now we just need to divide both these numbers by 3. So then that means 1 per 2 seconds. Well, that's our definition. Remember, if we have one revolution, the amount of time it takes must be equal to the period. And that's what we get over here. Okay, so if you've got an RPM, the easiest thing to remember, if you want to turn RPM, is go 60 divided by the RPM. Okay, slap that in, you got your answer. Remember, this sort of reasoning and proof you will not get bonus marks for on an exam, so you don't necessarily need to memorize it. It helps if you understand it, just because it will help with your intuitive response to questioning. But you know, if you can memorize a formula, if it's just one of the 5 or so that you need to walk in with just stuck there in your head for you to write down as soon as you get the chance, that's a fine way of tackling it as well. Alright, let's have a look at this one. We have a car tyre has a diameter of 630 millimeters and is being rotated at 800 RPM on a tyre balancing machine. That doesn't actually matter. So we just know that it's rotating at 800 RPM. Determine the average speed at the outer edge. Okay, so let's draw this. We've got a tyre. Pencil. We have a tyre. It has a diameter of 630 millimeters. 30 millimeters. So D equals 630 millimeters, and it is going at 800 RPM. Now, 800 RPM we can't do anything with. We need to turn that into a period. Okay, we can work with period, we cannot work with RPM. So T, okay, so this is the formula we've got from our previous, is given time divided by number revs. Number of revs in this case equals 800. Revs per minute, that time means 60 seconds. So that T is going to give us 6 divided by 80. 6 divided by 80, 0.075. 6 over 80. If you wanted to, you could use 3 over 40. Sometimes fractions can be useful, especially if it gives you a weird answer. So don't hesitate to work with fractions. Either of those would be an acceptable answer. Now, let's go back to our wheel here. We have a diameter. We don't use diameter for anything. We need radius. Radius, remember, is half our diameter. So half of 600 is 300, half of 30 is 15, so that'd be 315 millimeters, which equals 0. Well, actually, it's just like this. 315 millimeters would be 3.15 times 10 to the negative 1 meters. Okay, or you could leave it as 0.315 meters. It's not a big deal at this stage. So we've got our radius and we've got our period. We need to find out the average speed. Well, in this case, remember, speed is equal to distance over time. We have a radius, which means we can work out a distance, because we need our circumference around a circle. Remember, you've got circles, we're going to probably need a circumference of something at one point in time. And we have a time here. And so we can work this out. Speed, remember, equals distance divided by time. In this case, 2 pi r over the period, because the distance is going to be one full circle, and for one full circle we need the period. So let's do that substitution. 2 times pi times 0.315 divided by 3 over 40, or 0.075. Let's chuck that in. 2 times pi times 0.315 divided by 0.075 gives us an answer of approximately 26.4 meters per second, which is 95 kilometers an hour, which is reasonable. I mean, I would expect a tyre to be able to go at 95 kilometers an hour. If it wasn't going at, if it was going something like 300 kilometers an hour, I might get a little bit concerned that my math is wrong. If it was going like 1,000 kilometers an hour, I think I'd be very worried about that. Okay, so we've got a suggestion here. So this is an interesting one. It is suggested that you can increase the speed of a dryer by doubling the diameter or doubling the rotational speed. Dryer A has a tub diameter of 50 centimeters and a speed of 1200 RPM. Dryer B, though, has a diameter of 100 centimeters and a speed of 600 RPM. So we can see here that A is half as big as B, but it's twice as fast as B. So we want to know which one gives the higher speed. Okay. Now the question kind of says, there's this suggestion here, so it's quite possible that we're going to find that these two will be equal. Okay, and then we'll look at part B after that. So let's do dryer A, dryer B. This thing has a diameter of 50 centimeters. This thing has a diameter of 100 centimeters equals 1 meter. That means that this has a radius of 0.25 meters, while this has a radius of 0.5 meters. Okay, we're trying to work out speed, so we're going to need a time. We can use our radius to work out a distance, because remember we've got a circle. Distance around the circle is 2 pi r. I'll just draw this up the corner. So this distance all the way around, that was a bit wonky. Let's use just d for distance equals 2 pi r, and we're going to need its period, because if we get the period then we can work that out. So we've got our radiuses, 2 pi r, we'll worry about that in a second. Now we have a RPM. This one has a dryer A is 1200 RPM, while this is 600 RPM. Now, to convert RPM into period, we need to look at the time divided by the number of revs. Now the time is 1 minute, so 60 seconds, divided by 1200 equals 6 over 120, which is 1 over 20. 60 divided by 120, oops, 1200, 0.05, yep, 0.05. While this one, T is going to equal, we'll just use that formula, 60 over 600. We can see it's going to be twice as large. Divided by 600 is 0.1. Okay, so now remember we need a speed. Speed is distance divided by time. We can work out distance. We need 2 pi r, and we've got a time. So speed equals distance over time equals 2 pi r over t equals 2 pi times 0.25 over 0.05. We get finally 2 times pi times 0.25 times 0.05. Speed is approximately equal to 0.0785 meters per second. That seems quite slow, but it is what it is. Let's look at the other one. Speed equals 2 pi r over t equals 2 pi times 0.5 divided by 0.1. 2 times pi times 0.5 divided by 0.1. I've done something wrong there. 2 times pi times 0.25 divided by 0.05. I must hit a multiply. Don't know what I did there. Let's get rid of that. 31.4 meters per second. That seems much more appropriate. 2 times pi times 0.5 divided by 0.1 is speed equals 31.4, and so we would conclude that they are the same. Note, you would actually have to finish with that sentence and then say that they are the same. Therefore, same. Even that would be enough to say that you've now answered question 1 for part A, which is asking you to determine which dryer gives the highest speed. Determine is often a single point response on some questions, but in this case, because we're asking you to compare, there's an implicit comparison, this would be worth more than 1 mark. You wouldn't be doing all that work just to get 1 mark. So now second part is propose, which would be preferred for a household laundry. Now the thing is, if they're both spinning at the same speed, then they would get our clothes dry at the same speed, I imagine. Let's maybe go back and consider then the physical properties. Well, this one has a diameter of 1 meter. That means it's a meter across. Well, this one has a diameter of only half a meter, so this one could fit in a smaller space. But it does go faster, so maybe to make more noise. This one is bigger, but it goes slower, so perhaps it doesn't make as much noise. So the question would be then, what's suitable for what house? And if you turn around and said, this is smaller, better for apartments, okay? This is larger though, better for bigger houses where you've got enough space to fit a big load of laundry in. Because remember, if this only has a diameter of 1 meter compared to 0.5 meters, you can fit a lot more laundry in that than you can in that. Because when we're talking about surface area here, and then we would have the depth of the, because it's a cylinder. Surface area increases proportional to pi r squared. Sorry, or cross-sectional area increases proportional to pi r squared. So even though if it's doubling, it's actually an increase in volume of 4 times. Hey, we're doing a bit more mathematical testing on different things. Okay, these next few questions are part of chapter 3.3. So if you want to find those questions, I do skip 3.3a because it's just a fairly straightforward difference of vectors, and we have done that reasonably recently. Remember, this textbook is based off the idea that you've done linear motion way back in previous year 11, and then you're not getting to this until sometime in year 12. So that's why they're worthwhile having a look at that, just to make sure you wrap your noggin around it. So let's go down to 3.3b. A rubber stopper on a piece of string 1.5 meters long is whirled in a horizontal circle at a uniform speed of 2 revolutions per second. So we do have another unit here that we didn't see before in our theory, but instead of going revolutions per minute, we have revolutions per second. So converting that to a period, we are going to have to sort of consider that a bit. This would be what we call frequency, by the way, in that it's happening twice per second. And we've got a couple of things to calculate, so let's start off with that. We have our person, assuming there's a person in the middle, let's put that person. We have our string, radius equals 1.5, and then we have a thing going around it. Not a great circle, but we have here that we have a speed of 2 RPS. Let's convert that to period. Okay, we've got RPS, RPM, doesn't matter if it's revolutions, convert it to period. We can work with period, we can't work with revolutions per whatever. period equals time divided by number rev. Well, the number of revs is easy, it's just 2. We can see that number there. But now the question on the time, because before we had revolutions per minute and we were using 60 for time. Now we have revolutions per second, so we're going to have to use 1 for time. And so our period here equals 0.5. Okay. One of the really good things is that the revolutions per second is what we would call a frequency, but that's not something we expect you to pick up until we do waves later on. What's really good about it is that the relationship between frequency and period is just that they're inverses. So you can go, well, this is equal to f, we call that frequency, and t is equal to 1 over f. Feel free to memorize that. I do believe that one may be in your formula sheet, just in a different section though. We do need speed, so we're going to need to work out distance. So speed equals 2 pi r over t, because 2 pi r will be the distance all the way around. Finish all that off. So that distance equals 2 pi r. Speed equals distance over time. 1 revolution. Period is time of 1 revolution equals 2 pi times 1.5 divided by 0.5. 2 times pi times 1.5 divided by 0.5, and we get an answer of 18.8 meters per second. Great. Second step here though, now we would need to work out centripetal acceleration. Remember, speed is equal to tangential velocity. So we're going to need that. Now the formula we've been given for centripetal acceleration is v squared divided by r. And we have our v, we just worked it out, so that's going to be 18.8 squared. We've got our r, it's 1.5. We've got that here from our question, 18.8 squared divided by 1.5, and we get an answer of 235.6 meters per second squared. And you might be going, wow, that's like so much. But these will have quite significant values. But this is also a vector, so what direction is this? Okay, we know then, and this is an important thing, so you've got to keep this in mind, that the centripetal acceleration acts this way. It is center seeking, it is going to the middle. So I'm going to say to middle. Alright, so do not forget your directions when it comes to your vectors. Let's have a look at the next one. So this is 3.3c, I believe. So a rubber stopper of mass 20 grams is whirled in a horizontal circle at constant speed on a string that is 1.5 meters long. If the average speed as calculated in work example 3.3b is 18.8 meters per second, calculate the centripetal force and hence the tension. So, this is basically what we've done in class with our little, whirly thing here. So, we have our person, we have our object, the mass is equal to 20 grams, equals 20 times 10 to the negative 3 kilograms. Make sure we are converting to SI units. Kilograms is the SI unit for mass. Apologies, excuse me. V equals 18.8 meters per second, and we know that the radius equals 1.5. Now, the centripetal acceleration we just worked out a second ago, and we know that if we multiply centripetal acceleration by by mass, we will get the centripetal force. Okay, I'm actually going to write it like this: Fc equals mv squared over r. I don't like the F net equals mv squared over r because, while yes, it is a result of the net forces of things acting, it kind of loses the fact that you need to be able to work out centripetal acceleration, and you need to be able to recognize it. So I like this formula. Equals 20 times 10 to the negative 3 times 18.8 squared over 1.5. And we chuck that into a and we are going to get 4.7 newtons equals 4.7 newtons. Let's draw this so that we can think about the tension force. Okay, we would give this a symbol, so inwards or to middle, whatever you want to call it. So we've got this person's hand, that's a hand. We've got the rope coming out of it, and we have the mass on the end. Something is pulling that inwards, the centripetal force. But we can also feel on the hand something is pulling it outwards out of our hand. This is the tension force. Okay, the tension force, remember, is the sum of the continuation of forces inside this apparatus, or this connection that is at tension underneath between these two objects. So in this case, tension is actually quite easy. The tension force in the string is going to equal the centripetal force. So Ft will equal Fc equals 4.7 newtons. Because it's tension, and tension acts in both directions at the same time, we don't worry about giving it a direction. Okay, tension is technically a scalar, but we don't, because it is a force, we're not really worried about it too much. But in this case, just consider how the fact that our tension is equal to our centripetal force, because this tension is what's causing this centripetal force. If this tension was too high, the string would break, this object would go flying off. If there wasn't any tension, nothing would be pulling this object in, it'd be going in a straight line. So the tension is what's causing this, this centripetal force to appear as we're changing its direction. Okay, worked example 3.3D. We have here a motorcycle rider of total mass with a total mass of 1250 kilograms, traveling constant speed around a dry circular track of radius 50 meters. Calculate the maximum safe speed. So we have here that there is some how do we explain this best? First off, I'm going to draw this. We have a road, and we have our motorcyclist. I can't draw bikes. Okay, is going around this path. It's changing its direction. We'll assume it's going constant velocity. We'll say that v equals unknown, but we do know that it is constant because we're told that it's going at a constant speed. It has some, what's the word I'm looking for? Some force that is pulling it in. Okay, and that force that is causing it to turn is friction force. Force due to friction. Now, the text actually gives us a useful thing there, where it says for car with rubber tires on a dry bitumen road, friction is typically equal to 70%, 0.7 of the car's weight. So in terms of that force that is pulling us down, we need to consider, well, instead of it being mass times gravity, which is 1250 times 9.8, so somewhere close to 1100 newtons, we need to just get 70% of that. So this friction force is what allows it to turn in. If friction's not enough, the bike doesn't follow the path, it veers off, or the bike will skid. Okay, you can see this really easily whenever some idiot puts their acceleration pedal down really hard at a stoplight, because the friction is not high enough to resist the rotational force. The tyres squeal and they spin out. As soon as the speed drops to the point where it can then grip again, we then get motion, which is what we want. So this frictional force, and this is the hardest part of this frictional force is equal to the centripetal force, because this frictional force is causing this turn. If these things were not equal to each other, you would not be able to make this thing turn. Okay, frictional force might end up being higher But if the frictional force is ever less than the centripetal force, your bike goes sliding, your car goes sliding, your walking goes sliding. I mean, you rely on this to walk. So let's do some substitutions. We know that Fc equals mv squared over r. That's good. We need v. We have an m equal 1250. And we're told that the radius is 50 meters. So we've got two of these terms, so that's good. Sorry, two of these terms. The last question is, what is friction force? And we're told that the friction force is equal to 0.7 m times, well, mg in this case, because that'll be our normal force, our weight. We're told it's 0.7 of weight. This, not in syllabus, but there's nothing stopping you from using that as a foundational point to do some further exploration of yourself into friction. Remember, if I don't teach it to you directly, you can use it as an extension object for your student experiment. The first thing that really stands out here is the fact that we have mass on both sides. The mass term is cancelled, and this is something that's really unintuitive to people, that if you need friction to turn or you need friction to move, friction generally doesn't actually depend on mass. So that's worthwhile testing if you wanted to do some testing on that. So we have here 0.7 g equals v squared over r. We're going to do some rearranging because I want to get one thing just to substitute at the end. Multiply r across, 0.7 gr equals v squared. Take the square root, v equals square root of 0.7 gr. And we can substitute because we've got numbers for those. So that's going to equal square root of 0.7 times 9.8 times 50, because we're told it's 50 meters. So 0.7 times 9.8 times 50, and we take the square root of that answer, and we get that velocity is equal to 18.5 meters per second. Okay, which is about 11 kilometers per hour. So it's actually, going reasonably slow. There is some extra information there. So for a wet road, the friction is about 50%, and for an oil patch, it might be as low as 5%. So those percentages can change, and that's worthwhile doing some research on that if you wanted to do anything with as far as friction goes. All right, I believe that's our last one. Yep, so in these last two lessons, I didn't put my point 3 in, I apologise. Let's write that in. 3 solved problems. So we did these first two success criteria in the last video. We've now done our third one. So hopefully at the end of this you can solve problems using some uniform circular motion. Remember, find the radius, find the displacement, find the distance, and convert any revolutions per whatever into period, which is an actual useful value. Alright, to finish off this chapter, please access the O-Book, download the 3.2 and 3.3 Check Your Learning PDFs. I've just given you a couple of questions from these, and you should be they're all 4 of them are calculations, 2 of them are describes. So from 3.2, please complete questions 2, 3 and 5. And from 3.3, please complete questions 2 to 4. Put them into the 2.5 space on eLearn. Thanks for listening, guys. Have a good evening.